Okay. Okay. Uh, Good afternoon, all. Again, welcome to my machine learning for material sciences. So today, Professor Sen is traveling, so I'll be present in the class. So I will continue from the where I last presented, and hope you have been doing like some of the exercises that Professor Sen has given to you. Specifically trying out data sets, downloading them, filtering them. Hopefully, you are doing more than what he has probably started with. Because all that is important to basic understand where, because only when you have an idea, because data set should be the least of your worry. Matlab, it is actually of primary worry if you do machine learning, but at least access to those data sets and how to use them probably like that should not be like a matter of concern later. Yeah. So that's why also we have talked a lot, and then we have tried to design the course in a way that we spend as much as time as possible to make sure that at least access to data set is not an issue. Yeah, this is required both for your projects as well as other things. Hopefully in your future work. Yeah. So from the machine learning point of view, I just want to give a quick review. So what we have done till now is basically we have looked at artificial intelligence as a whole. We have a like a very uh, like how do I say very naive definition, but that works. That's powerful too. And then we looked at like how we can do machine learning as a whole. And then one of the ways you can do no, one of the ways you can achieve artificial intelligence is through machine learning. And then we looked at some of the algorithms in machine learning, basically like types of machine learning, and then some of the algorithms. Initially, we looked at supervised algorithms where specifically both the data set, like the observations or the examples were there, as well as the corresponding label to that example was there. And then we also looked at some of the algorithms that specifically worked where there are like the observations are there, but the corresponding label is not there. Yes? So both of them, like as in, very important. Like both of them have their more advantages and uses. And in the meanwhile, also we looked at something called gradient descent, which is the algorithm to basically to find the parameters that uh, make your machine learning model a model, right? Uh, we and anything belonging to the model that we can learn directly from the data would be like parameters, and anything that we learn a little bit indirectly and somewhere our choice or bias comes into picture would be hyperparameters that we have learned. And then after doing supervised and unsupervised learning, we moved on to some other parts of machine learning. Let's say one of the parts was like feature engineering, where we understood, like, given a categorical data, how to convert into continuous to categorical. What if you have data missing? What do you do? How do you make sure, like, what are the other things that you need to consider? Uh, uh, like, do you need to Mm, how do I say? Huh. So, for example, like the bias and the variance that you need to consider. And if bias is high and the variance is high, what do you need to do? And what is like a very good algorithm should have what? Like low bias and low variance, right? We looked at the regularization on top of it. And then we also looked at how do we approach regularization through, let's say, lasso ridge or L1 and L2. And I told you there are some other methods that we will talk about when neural networks come to picture. That day is not today, but sometime in future. And then the remaining thing was basically we jumped on another variant of this, specifically called ensemble algorithms, where we specifically looked at how can you combine many, let's say, many models together so that they become stronger. Right? So that was the entire probably like what we wanted to gain out of this, at least classical machine learning, let's say. Yeah. They're all super useful techniques. They're all very powerful. I've told you again and again that the classical algorithm might seem classical in the like the word, but they are very powerful. The first algorithms you should definitely try is those algorithms. because whatever comes after that, of course, they are super powerful when they work. It's the one that will be starting today also. But making them work is also a challenge, which is way easier doing it in classical algorithms, right? Fine. So with that, basically we have done supervised, unsupervised, bias, variance, ensemble, uh, some form of feature engineering that we talked about, right? So now we jump on to neural networks. Yeah? So this is of course a little bit how do I say, a little bit different, but it's not that different. Those concepts are borrowed from the same principle. Uh, Same gradient descent you will see, same bias and variance you will see. Um, the only thing is probably this has become more powerful because you could parallelize this particular algorithm, and this is inherently a low bias algorithm. Basically, it does not, how do I say, assume anything about the data itself. Yeah? Fine. So then to start with, so neural networks again. So we today we'll just try to, like, as in, build a very slight foundation on uh, where did the neural networks come from. This might not have been like super well understanding of the source, but and some parts of the history I don't have much because I don't remember either, so I just put one slide, and then we'll talk about the smallest possible available neural network, that is like perceptron. Yeah, and hopefully like we will understand how a neural network works through one of the through a single neuron. Yes, mathematically, and why it does what it does. Yeah, and what are the like limitations that surround it. Yeah. Uh, okay. So now we go ahead. Okay. So the first thing is, of course, like it's a neural network, neural brain, neurons. Yes, so it has come from there. So the only thing is, it's not straightforward exact thing. But yes, but the intuition definitely has come from the biological neurons, right? So everything I'm speaking, that comes because some of the neurons are firing in my brains. You are hearing because some of the neurons are firing in your brains. You are seeing because some of the neurons are firing in your brains. Yes, I am moving my hand because some of the neurons are firing in my brains. So then, how does a biological neuron look like? So there are dendrites. So the stems that come out of particular, it looks like it's a tree and a flower. I hope you remember your biological lessons. So dendrites will be wherever they receive the signals from other neurons. Cell body is where we process and integrate our other signals. Axons is where we transmit our output. Yeah? And synapses is where how we control the signal strength. Yes. And the only, it's not that you have to remember this dendrite, cell body, or axon or synapses, is that what do they, like, for example, a single neuron can have thousands of dendrites. That means it can receive a lot of signals from all other neurons. Yes. Cell body, like, of course, somehow it integrates all the incoming signal into one and then provides, either I have to send further signal to other neurons or no. Yeah. Axon is where basically if I have to send signal to others, this is the way. Axon is the one where the electrical signal travels to other neurons. And then synapses are there. Synapses, the most important part is that basically controls the signal strength. So our neurons basically relay message also, and the way they relay message is by either the synapses are strong, that means the signals are getting amplified, or the signals can be dampened, or basically the signals can be weak. Yes, and this is exactly how we've abstracted the biological neuron and then we pushed it to basically an artificial neuron. Okay? So artificial neurons, the abstraction looks like this. Yeah? Mm. So instead of dendrites, what we have is basically inputs. Yes, and the inputs are basically numerical inputs. So in a real problem, like these might be, for example, pixel values in an image, or like the features like, let's say, temperature, humidity, yes, or time of the day, yes, in a weather model, right? So these are all inputs. Yeah. And weights, for example, these are all synaptic strengths. Yes, so this is a large positive weight will mean here that we are sending that this is a very important signal. This should be basically amplified. Uh, and a negative weight would mean like probably this will end up in basically rather inhibit activation or probably deactivation, though we don't tell. It's just basically the activation does not happen. Yeah. Like weighted sum and bias is basically the weights, the signal multiplied with their weights when they come to us. Basically, this is, and then we add some kind of bias that the neuron has, let's say. This is what we think that the cell body is processing. Yes. So assume all a bunch of inputs are coming, the and in the cell body itself there is a some kind of summation and the addition of bias takes place. That is what we correlate to thinking, yeah? Or like the processing. And the last is basically activation function. This is basically the actions that release the information from the cell body to other neurons. But these actions can be either activated or non-activated. So uh, activation functions equivalence to like an action firing threshold, right? So there is a nice correspondence, but I still have a issue. Maybe like it's not super biologically true. Maybe the like the our artificial neurons, but that's okay. This the point is basically we got the intuition, and also like magically this has also worked. It's not like it's not so that's the intuition behind why we have neural networks the way we have. Yes. The next one is basically some historical context. Like you need not remember it, but like some how do I say landmark contribution to why it is so. So one of them is like Maculo and Pitt's neuron, 1943. Let's say it was the very first mathematical model of a biological neuron. It has just a binary threshold of activation. Yes. Then we have so they proved that you can build logic gates. Basically, I don't know if you remember logic gates. Like most of the electronics that we have are logic gates. So all the transistors that you have heard, yeah. And so they proved that you can build logic gates with these neurons. So basically, they show that the networks of artificial neural networks could compute any logical function. Yeah. So this was super huge, right? So basically, this told that okay, now neuroscience to competition, they basically established a bridge. Yeah. The next came is like Rosenblatt's perceptron. So they basically made it real, let's say, because Macaulay-Pitts was still a mathematical model. It was not formalized, let's say. So, but Rosenblatt basically, Frank Rosenblatt, let's say, he actually built a machine called Mark I perceptron at like kernel. He introduced a way that we could also learn, as in the way for a machine to learn the weights. Yes, from examples, let's say. So this was probably the first, let's say, learning algorithm was introduced. Yes, and otherwise, people initially thought that okay, the weights has to be handmade. For example, if the inputs are coming and the inputs are going out, like do you need to? We need to understand the actual situation and then put on weights. This is fine if you have just a single neuron, but imagine like trillions of neurons, you just cannot keep on assigning weights, right? Because one change in a weight affects rest of the trillion. So the next is basically 1969, let's say, uh, and Minsky and Papert. So this is where again like things got a little bit more interesting. So they published a book called Perceptrons. Basically, that mathematically proving okay limitations of single layer perceptron, what happens, and their most famous example was XOR problem. We'll also talk about this in a little bit. And they basically showed that a single perceptron, however powerful, like the previous author basically was telling key, okay, you could solve any logical problem, but it seems like a single perceptron cannot solve a simple XOR problem. Yeah. which is a very simple logical function. So the moment this paper was published, like people gave up hope on, let's say, neural networks as such, not AI per se, but neural networks. But because neural networks were driving the AI, then it moved on to be called as AI winter. I think Professor Sen talked about you in the very first class. Yes. Uh, so basically, one paper basically froze the research in this particular area in the field because somebody told, okay, perceptron cannot solve simple XOR problems. So now, what happens in again 1980s? Backpropagation came. Basically, researchers they discovered or rediscovered backpropagation, which is an algorithm to train, let's say, multi-layer neural networks, and suddenly, like we could solve XOR-like problems. Yeah? So then multi-neural networks basically now can learn very complex problems, nonlinear patterns, and this has basically set the foundation of, like, let's say, modern deep learning. Yeah? Generally, whatever the papers you would have seen from 2010 and onwards, generally they depend on this. It's not that the classical learning has died out completely, but problems like we have been able to tackle more complicated problems with the help of basically deep learning. So the idea was the math was previously there, the machine was there, the deep layer, and then hardware, more data, more compute, and some clever tricks, right? And the clever tricks are getting invented day by day, every day. So, for example, ChatGPT, and I hope you have heard about DeepSeek. So they introduce also very clever techniques on how to train very large language models also. So these tricks are continuing getting applied. Uh, More data is getting collected, more algorithms are getting developed. But typically the journey has been like this, right? So biological to maths to learning algorithm, one perceptron. Some papers saying that it's not enough. Then people have found out, okay, we could do better. We could actually solve XOR, and then so on and so forth. Okay. Okay, now we'll just we have covered this one, but these are two things that were essential, so I put it here. So one of them is like what is a vector? So a vector is again an ordered list of numbers. In machine learning, a data point is a vector. Yes, so a single data point, like a person, will be a vector. Uh, and for example, if you're predicting housing prices, uh, so the vector could be like the house itself is a vector. It's a data point, but that is like how much, like the area of that house, number of bedrooms, what is the age of the house, how old it is, let's say distance to airport and distance to railway station. Yes, those are all the factors that tell you about the data point. And the next fundamental thing that we have, I think in machine learning and deep learning, all we do is dot products. If I say, it won't be very far. So the dot product is one of the most fundamental operations, and so the way it is represented is this one, like W dot product X is equal to summation of W and Xi. You have weights for every dimensions multiplied with itself, like each dimension of the input vector or the whatever the vector is. Yeah. And geometrically, the dot product will basically measure how much the two vectors in point in the same direction, right? Or you have two vectors, how much are they in the same direction? Yes. If they point in the same direction, you will get a very large vector. If they are orthogonal to each other, like or opposite directions, and then they will give a very large negative number. Say if they're perpendicular, they will give zero. That means they're not pointing. Negative will give a very, let's say, large negative number. If they're same direction, large positive. Perpendicular, zero. Yeah. Okay. Uh, okay. And okay, so generally, I hope you can see then the reason why dot product is very essential, right? So technically, if I want to ask, like, can you try to find another person in this world who looks like me? So you technically can tell that if I am my face picture is in data point, I could if I could do a dot product with every other face, and whichever dot product gives me the maximum positive value, that is the closest. Yes, and that's how the intuition comes, right? And that's how the dot product is very essential. If somebody looks exactly opposite of me, it would give a very negative number. Yeah. So on. Yeah. Another example is like, for example, email is spam, right? So, and the weight vector W might have very large positive values for positions to we discussed this in SVM also. Like, let's say the weight also like has very large weights for words like free, click here, winner, yeah, and it will have very large negative values for normal words. Let's say hello, yeah, hello Shubhankar, like how are you doing? All that stuff will be like very large negative numbers. Those are very normal words. But for free, winner, and click here, they'll have very large height. So us wait for those values and those spam then matches, and then you get a very large number. Yeah. Okay. Now the next thing. So I hope that makes sense why dot products are essential. The next is basically the matrix vector multiplication. Uh, so matrix will be like just a stack of weight vectors, you can call it. Hmm. Uh, so here, what do we have is basically we have a matrix which is just a collection of, let's say, other vectors. Yeah. Uh, so, and why is this like each row here? For example, like let's say W is a like let's say it's a column vector, let's say, and then X is your feature vector. You multiplied it, you got a like a W1X and W2X, and X is a vector also, right? So this becomes like a matrix of weighted vectors, whatever is on the figure. And then the multiplication itself gives you a vector of outputs. Yes, and if you consider the W each row of W to be weight vector for one neuron, then the multiplication WX will give you a vector of outputs one per the neuron. Yes, we will come back to that again. We'll see how that affects again. But but then why do we care about this matrix notation? The first is basically it's easy. Somehow all of us understand tables pretty well, right? So humans are like super good at understanding tables, I think. Uh, one equation and then one equation also, like it's a very simple equation that can describe the whole operation for all the neurons. We don't have to do it multiple times. And also GPUs that have been built, they were originally built for graphics processing, but eventually all they do is like matrix multiplications and all. I would not say matrix multiplications only. All matrix operations are generally fast and efficient. This is the reason why a matrix is preferred. And most of the modern neural networks are basically sequences of matrix multiplications in some order. But it's not that the matrix multiplications is the only thing that takes place. You have something called activation functions and all that stuff, concatenation, all the other operations are there. But matrix multiplications is where the major compute happens. Yeah. Okay. So now let's go to our perceptron. We have sorry. Um, sorry. Yeah, sorry. So we land up at perceptron model basically. So the way it looks like is very simple, but it's very important right now because deep neural networks, yes. What we have here is like y is equal to f of wx plus p. Yes, this looks very similar to the previous things that you might have seen. Yes, but this is how the perceptron also looks like. So here x is basically a input vector. This is your data maybe. Yes, you can consider if this was an image, let's say, you couldn't consider like an image as let's say this is an image which has, let's say, 4 pixels, two on the top, two in the bottom. Then if you can separate out of all of them, like we can linearly flatten the thing, that will be 4 pixels. Yes, so that means those 4 pixels can be the input vector. Yeah. If it is a 28 cross 28 pixel image, then you will have a 784 dimension of the input vector. Yeah. So that is what goes inside as an input vector, that is your x. Yes. Then what you have is the weight vector. Weight vector is basically nothing called a learnable parameters. This is what the perceptron adjusts. This is what perceptron while learning modifies. Yes. But also you can think of in the other way. Basically the weights, they basically encode the pattern that the neuron has to learn. Okay. Or they can these are the weights encode the patterns that the neuron has learned to recognize, let's say. Yeah. Now the dot product is there that calculates the similarity score, how much the input matches with the weight. The weight here is the pattern, so how much the input matches with the pattern. Yeah. And then we have the bias. So the bias is basically a threshold adjustment. Uh, Without this, basically the decision boundary always has to pass through the origin. With bias, we can shift it anywhere. Okay. Um, so the way it becomes, like, for example, if it is zero, like it is always zero, then the neuron does not have a hold, right? So basically neuron says, okay, if you're greater than zero, I have to fire. If I move bias to, let's say, 5, it neuron basically has a hold on it. So it tells that even if there is no input, even if there is a minor noise, the value can go beyond zero, right? So then it will just fire. Rather, if there is a bias to, let's say, 5, then small noises it can avoid, and it can have a control on where I am able to fire, right? So that's what the bias helps, like without any input, or you can talk about it in the terms of without depending on the input. Uh, Neurons like ability to fire when. Okay, and that's the bias. Because if x is 0, then it only depends on the bias. Sorry. Where the next we have is y. I'll come back to f in a bit. Y will be the final prediction. So, for example, if we have to do like binary classification, let's say, then it can predict with the 1 or it can predict with the 0. Yes. Similarly, we have done SVM logistic, all those things. Same principle. Now, you see the function f. The f here is the activation function, and that's basically a decision rule that basically takes the wx plus b and somehow tells either the neuron has to fire or not fire, or has to activate or not activate. Yes, that's why it's called activation function. And expanded form is basically whatever you have seen before. It's basically summation of w and x. Yes. Fine. And so basically what this perceptron is trying to do is basically trying to compute a weighted vote. Yes, it's asking everybody to vote with their values, and then a weight is being applied, and then the bias basically adjusts the threshold, and based on the total vote, if the vote exceeds 0, it will fire. If it is below, it will not fire. But that 0 or the other thing also depends on the f. Sorry. Fine. We will talk a bit about this activation function. So this is the function that makes the neuron, basically single perceptron or the neuron, to either to fire or not fire, or basically tell us what decision it has come to. Yes, given all the inputs and the weights and the bias, all of these has been given. What is your final decision? That f is what determines. Yeah. So the function that you can see, it's a very like it was Rosenblatt's original choice. It's very simple. If z is greater than 0, make it 1. If z is less than 0, make it 0. It has only binary output, 0 or 1. But the only problem is it's not differentiable, right? It's not a continuous function. It's not differentiable. Uh, uh, then what do we do? So basically the gradient descent algorithm that we have, which basically requires the function to be differentiable to calculate the gradient and then flow the gradient back. So the perceptron learning algorithm basically here, it's not learnable. Yes. And also it creates a very hard decision boundary at wx plus b is equal to 0. Yes. This is like a step function, I hope, like 0, and then at the beyond 0 it becomes 1. Yeah? Uh, and this is a older function, of course, like right now we do not use activation functions like that. Yes. So what's next? So the next one is something called a sigmoid function. Yes. This was the next step. Basically, instead of having a hard decision boundary, it basically has a very smooth curve or a decision boundary. We have seen this in logistic regression as well. So there are many advantages to that. No matter what is the input, you will always get the output between 0 and 1. Yes. Logistic regression, I hope you remember. And because the output is between zeros and ones, this is like super nice for probabilities. Yes. And you can also treat it as a probability in the terms of like sigma of z is equal to probability of like sigma of whatever the z, let's say, is equal to probability of class being 1 given x. Yes. um, you can treat it like that. Probably exact definitions will differ as we go. And of course, this is smooth and differentiable. We saw in logistic regression, you can use logistic regression to solve, sorry, gradient descent to solve this. Yes, to find the parameters, basically to find W and B, you can use gradient descent can be used to find this. Yeah, if the activation function is sigmoid function. And the next is a derivative. Also, derivative is also very simple. It's basically the same function itself, right? It's become sigma z multiplied by 1 minus sigma z. So technically, we are not calculating any new values. So if we just keep a track of the values itself, the gradient is gradient, whatever the value of the function is multiplied by 1 minus that function. So it makes calculations also super efficient. Yes. So advantages, of course, like, it has like probabilistic interpretation. It's very nice, right? So as in, you don't have to just say that the email is spam or not spam, because there are many cases, right? So you tell that there is a 92% chance that it can be a spam. Yes. Which one is more realistic, right? You don't say like, okay, this is definitely a spam. That would help, but it's very hard to tell. So uh, and we can set also different thresholds. Okay, if anything, if the model is not absolutely sure, that is 95% sure that it's a spam, don't make it a spam. Yes. The problem here, there are few. One of the problem is basically if the z is super large, what happens is basically the sigmoid will saturate. That means its output will be very close to either 0 or 1. Yeah. And what happens then, that the sigmoid becomes uh, basically very tiny, but the gradient itself will become tiny. Yes. Uh, Now, because it will be like sigma of z will be 1, and 1 will be very close to 1, and then 0.99999, let's say. The gradient is basically that multiplied by 1 minus that. So it will be 0.99999 multiplied by 1 minus 0.99, which is basically 0.0000. So eventually multiplication of these two values becomes very small. Yes. So remember, you have like, let's say gradient has to flow back. Let's say here it doesn't flow back too many times, but if you use a sigmoid and you calculate a gradient is what that tells, okay, to reach to this particular part, you have to change it by this much. But if the gradient is too small, the direction it is asking you to move, that direction is okay, but it's telling you don't move very far. So that means the movement to the correct place will be very less, right? So basically, because it is compresses the large values, so it causes something called a vanishing gradient problem. We will learn about this again a lot more in detail. Another thing is basically it's not zero centered, right? So outputs will always be, let's say, positive. Yes. This can cause issues. So basically, some optimization techniques, if you use, they might have issues. And like if there is always a positive thing, it will keep on jumping rather than reducing. Yes. So positive, it's if it is not zero centered, that has other issues. Yes. But sigmoid is also very useful, matlab, as in I told you, probabilistic interpretation and then logistic regression is also used, and also used in other binary classification methods. Sigmoid is used, yes. Now there are of course a little bit more popular ones. But one of the other thing is basically that solves the zero centered problem is basically the tanh, yes. Uh, the tanh is defined by this. Tanh is equal to e to the power minus e to the power z minus e to the power minus z by e to the power z plus e to the power minus z, right? So that is, you can also say that 2 over 1 plus e to the power minus 2z minus 1. And this is better than sigmoid's 0 comma 1 because it's basically centered at 0. So it has both negative values and both and positive values, and they have equal representation. It's not like a minus 1 to 10. Yeah? So it's minus 1 to 1. Like both are well represented, both the positive and the negative values. And mm, that is one advantage, of course. And then because the gradients then can flow both positively as well as negatively, right? So it's more balanced optimization. You don't always have to subtract grade because the negative gradient is what we subtract, but what we do here we can do also some increase in the weights, right? So it makes like a way better optimization for optimization through gradient descent at least, because update can go in all directions, positive as well as negative. Yeah. And derivative is also very nice. If you look at this, like it's same, almost like 1 minus tan square z basically, tan h square z. So if you remember the tan h function itself, we just square it up and subtract it from 1. So it's very nice also. Yeah, it's then tan h is basically, you can understand, it's just an improved, let's say, sigmoid, which has the same smooth differentiable properties, but it's zero centered. Yes, that's the advantage. And tan h is still used in some context, specifically in recurrent neural networks. As much as I remember, there it is used uh, for basically modeling sequences. And but for feed forward networks, we have moved on a little bit. Tan h also will suffer from the vanishing gradient problem. At the very high value of z, it is closer to 1. Low value, it will be like minus infinity is closer to minus 1. So same problem will come. It solved only zero center issue, but the large values of z, it will still be like vanishing gradient. The gradients will become very small. So we have moved on to something called a ReLU. Yes, most of the algorithms that you will see if you're reading papers right now for your project, you should be able to see that they might have ended up with something called a ReLU. So it is called a rectified linear unit. Yes, uh, it's I think it's like a dark magic stuff that is happening because it's way too simple, but it works very nice. Yeah. And it generally, like nowadays, the most default choice. If you don't know anything, you start with this. Yeah, it's not that this is the only thing that is getting used. There are many variations of ReLU that get used. So ReLU is given by this max, or ReLU of, let's say, any number z is same as max of 0 comma z, and it's basically if it anything, if you can think of a axis, anything greater than 0, it will have its own value, that is equal to its value. Y is equal to x for anything greater than x, and if it is anything that is negative, it just makes it 0. Yeah. So basically there is no upper bound. If the input is positive, output equals. If it is negative, output is 0. That's it. Yeah. So output range is 0 to infinity. Yes, it's super computationally efficient because there is no, it is just equal or 0. We don't do much calculation at all, like e to the power z, no exponential, nothing. Yeah. Uh, and so derivative is also like ridiculously simple. Derivative is either 1 or 0. Okay, so again, super fast, super efficient. Um, but of course, it is non-differentiable technically at 0. Uh, but you don't have to think a lot here. Technically, you can choose it to be 0. That is what we have done here. Yeah. So at particularly, there is a non-differentiability there at the point of 0, let's say, plus minus like plus delta. But we can just pick it as 0. Whenever it is there, we are confused if it is non-differential. It comes to that particular point, we just pick it as 0. That's okay. If we pick it as derivative as 1, that's also okay. Because we choose this also, back propagation becomes super efficient. Yeah. And uh, yeah. So the next is first is solves vanishing gradients, because you see the z is till infinite. Yes. Second is if it becomes negative, it becomes 0. So if we assume uniform distribution of positive and negative neurons, half of the negative neurons will not even get activated, right? Because activation function for anything negative is 0. Yeah. So it's very sparse, which makes it very computationally efficient. Because at any time, only half the neurons fire. Yeah. Uh, and also it is closer to brains in the terms that neurons do not have basically an understanding of a negative firing. So if you consider biological neurons, like they either fire or they don't fire. They don't have a notion of negative firing. What does negative firing mean? You pull the information back. That's you don't do such kind of things. Yes. So either you basically are activated or you stay silent or dormant, right? So it's more closer to, let's say, biological neuron. That's one of the thing. But however, if uh, it still has that problem, if you get super negative values, its gradient is 0. So a very super negative value, there is no change in its value because the gradient itself says it's 0. So the term is called a dying ReLU. Sorry. So there are other methods that are used. There's something called a leaky ReLU. I will talk to you about this a little bit later when we come to that. But most of the new neural networks, ReLU is a very fine problem to start, like a fine activation problem to start with, activation function to start with. Yeah. Okay. So now the geometric interpretation. So the way it happens is the perceptron. Sorry. Sorry. So the perceptron will create a basically a hyperplane wx plus b. That will basically be in a hyperplane in a 2D. In a 3D, it's a plane. In higher dimensions, a hyperplane. Now it behaves like at least the hyperplane behaves like a SVM we have learned, like the top one basically becomes +1, below one is equal to 0. But we don't, how do I say, we only tell it because it becomes class of 1 if it is greater than 0, if class of 0 is less than 0. But here we still have more variations in this compared to SVM, let's say, by using activation functions. And fine. There are a few things. I will come to that when I talk about longer, like bunch of perceptrons. But then perceptron learning algorithm. So it is very simple. Uh, so let's say we have a bunch of examples x comma y. We want to know what is w and what is b. We first initialize weights randomly. Let's say w is equal to 0. For each training example, let's say xi and yi, we compute the prediction. Let's say yi is equal to f of wxi plus b. If those predicted value and the actual value don't match, then we update the weight and update the bias with the help of the gradient. Fine, that's all we do. Similar to gradient descent, yes. And we keep on repeating till there is a convergence. Convergence as in the yi is equal to yi. Basically, y predicted will be y actual. Or if we set our maximum number of iterations. Yeah. Uh, so here the error is basically a y actual minus y predicted, and the update rules I have told you. And what we try to do is basically every time we see it to be predicting, the weight basically changes, and the bias changes, weight changes. So we move it. If it is a false positive, we move the boundary away from xi. If it is false negative, we move it towards xi. Okay. Sorry. The next thing is like the convergence theorem. Convergence theorem is very like simple. I think you can also prove it. It's not very biggie. It just says that if training data itself is linearly separable, then the algorithm that we discussed here is going to converge. Sorry. Mm. Assuming everything can be correctly classified with a line, the previous algorithm that we discussed is going to have a is going to converge in a finite number of steps. And the number of steps that it can take is basically r square by sigma square. Let's say this is the guarantee we can have. So that means if the data is linearly separable, that means you can put a hyperplane between two classes. Then, and if you use this algorithm to find out the W and the B, then it will converge and you will find the W and B with at most this many number of basically iterations. Yeah. Fine. So I think it's already 5:23, 5:25. I'm also coughing a bit. So we will discuss. So today is this much. So we discussed on perceptron, biological notion. From tomorrow, I will start with this XOR and then we'll, oh sorry, on Friday we'll do it again. So I'll start with this XOR problem. Why the perceptron is able to be simple, powerful with activations, but then this was the paper that basically told it cannot even solve this simple logical problem. So we'll start with this. Yeah. Okay. Any questions before I leave? I will wait for like 20-30 seconds maybe if there are any questions. Okay, while people are typing, open review, I have received 3 proposals from the teams, and only one team has responded for their reviews. So other teams, please start on because otherwise there are no marks and passing will be extremely difficult this course without that. Okay, fine then. As there are no questions, so we will meet on Friday 4:30 to continue. Yes. Okay, I will see you then. Bye.